So I'm here to present joint work, adaptive random Fourier features with Metropolis sampling. It's actually a paper we recently published that did with Akku, who's here today, Mattias Sandberg, I think he's also here, and Peter Pleschak and Anders Pessi. Okay, so what are we up to? Well, let's start very simple. We do supervised machine learning, and we're trying to reconstruct the function. So we assume here that y is equal to f of x plus some noise term e, and f is the function we're trying to reconstruct. We, well, let's assume x and e are independent random variables, and as usual, sort of mean of the noise is 0 and it has some finite variance. We observe x and y for simplicity and independent samples. Not super important. And we reconstruct the function beta of x by solving a quadratic minimization problem. So far, all standard. Now, the first thing to sort of decide on is how to parameterize beta. And in this work, we are looking at a shallow neural network. By shallow, I mean there's one hidden layer, meaning we can write beta of x as a finite sum of some beta hat times some activation function of an omega times x here. Just sort of introducing notation. Boldface omega is a KD vector. Beta hat are the so-called amplitudes, omega are the frequencies. And the reason for calling them such is that we are working with trigonometric activation functions. So S of omega times x is just e to the I omega x. Okay. Okay, so what do you want? Well, we want to train the network, right? We're introducing here a small Tikhonov penalty, but basically we look at the quadratic minimization problem, and we are trying to minimize some expected value. So minimize the expected square distance between y and the function beta would give us beta hat and omega. And of course, if you plug the expression of beta that we had on the last slide into equation 1 here, you would see that the expression is convex in beta hat, but not in omega. And well, what do you do? I mean, this is, of course, familiar to all of you. Well, typically, you would try to solve equation 1 here with some stochastic gradient descent method. Maybe Adam, maybe vanilla stochastic gradient descent. And okay, so let's try that. Okay, so this is now a very concrete example. We assume here that there is no noise. F of x is given by the so-called sine integral times e to the, it should be, there's a typo here, sorry. Should be sine of x divided by a times e to the minus x squared divided by 2. Okay. A is a small number. In the example I'm showing you, we had 10 to the minus 3. And the reason, I mean, the sine integral really can be thought of as a, for our purposes, can be thought of as a regularized discontinuous function. As a goes to 0, it tends to plus pi half or minus pi half, depending on the sign of x. Okay, so we take the shallow neural network, we seed it with some initial choices of frequencies omega and amplitudes beta hat, and we run the stochastic gradient descent, and we hope to get a good, nice small error. And what we do more here is that we do that for successively larger and larger k. So remember, k now is the dimension of, it's really how broad the network is. So it corresponds to how many frequencies we use. And the capacity, of course, of the network increases with increased k. And what you'd like to see is that the more you increase k, the smaller the final generalization error becomes. Okay, what do you then actually see? Well, for small values of k, you do see an improvement in the generalization error as k increases. But at some point, that effect goes away, and the generalization error effectively flattens out. Now, of course, this could depend on exactly where this effect is happening. Where you see the flattening might depend on how you initialize the stochastic gradient descent, exactly how you pick the step size, etc. But this is the sort of result of an honest attempt to fit the network. It's not just picked so that it would produce a nice picture. Okay, so what's going on here? So it appears that at some point, increasing the number of frequencies does not lead to an improvement in generalization error. Why? Okay, well, let's just take a step back and think about the function that we're trying to reconstruct here. And the distinguishing feature really is that it has a almost discontinuity at zero. Now, if you look at the Fourier transform of f, that means that it really has pretty fat tails. There's a lot of energy in the sort of far away from zero. Just looking at a plot, this is what the right-hand side of the function looks like, and these two plots are the Fourier transforms of f. This is zoomed out, and then you zoom in. But the point is really that it's not going down to zero quickly. There is significant mass out here, far away from zero. Okay, so that's the Fourier transform of the target function. What about the Fourier transform of the reconstructed function? And how does it change over time? Remember, stochastic gradient descent is an iterative process, so we can be evaluating the Fourier transform at any point in time as we let the optimizer run. Okay, we initialize with some value. I think we used standard normal for the frequencies, so you get something like this. It's fairly centered around zero. Most of the mass is sitting between, plus or minus 2. You let it run quite some time. About 1 million iterations later, not much has changed. I think if you really drill down, you can see that it has sort of spread out a little bit, but most of it is still, firmly between -5 and 5. And of course, if you go back here, you can see that -5 and 5 is really not going to capture much of anything here. Yeah, sorry, the story continues if you relate around for a bit longer. Of course, we're not claiming it's impossible to reconstruct this function using stochastic gradient descent. We were unable to do so ourselves, but presumably with enough compute and enough time, this thing will eventually find all the larger frequencies as well. But as I said, we let it run for quite some time, so it's not just terminated immediately. Okay, so we have a problem in finer higher frequencies. Now, this is not something we were first to discover. And in fact, there's quite a bit written about this phenomenon lately. It sometimes goes by the name of spectral bias. I imagine that the phenomenon as such is well known to the community and has been known for much longer than the last couple of years, though. But I think the name spectral bias is fairly recent. Some people sort of claim that this is one of the reasons why neural networks work as well as they do, because this also has the effect of regularizing the trained function, because effectively you're ignoring sort of high frequencies. But for our purposes, it's a problem, it's not a feature. Okay, so having sort of failed with stochastic gradient descent approach, let's try something else. Okay, so starting with the minimization problem where we started, we assume now that omega is not any number, but in fact omega is a random variable. That means you can look at the mean overall. Well, you can look at the expected value of this with respect to omega, and you would expect to get something slightly worse than if you optimize with respect to omega. So basically, we're just using the fact that min is less than or equal to the mean here, and omega is now so non-boldface omega is a d-dimensional random variable with some density p, and boldface omega consists of k independent copies of omega. So here we're sampling, okay, the expected value should be with respect to boldface omega. Here we're just sampling omega k times with some density p, and that's what and then you minimize with respect to beta hat, and that's what you get. Okay. But of course, we can then minimize with respect to the density p as well. Let's just take a second here to look at the inner minimization problem here. So we've gone from this minimization problem to a minimization problem, a two-stage minimization problem, where for a fixed p, we're just solving the inner problem here. Now, as you remember, this problem is convex in beta. So for given density, or for a given sample of omega rather, we can just solve the normal equations and get this value. So really the problem now, if you want to minimize this, or the hard part really, is to find the density that minimizes this expression. And this typically goes by the name of random Fourier features. Of course, it's not strictly speaking dependent on using trigonometric activation function, the right-hand side here. I mean, it sort of makes sense for any activation function, really. Okay, now we have the unknown function f. That's what we want. Beta is trying to approximate f. Let's introduce f hat, standard Fourier transform of f. And let's recall the inverse formula. So we can, if we know f hat, we can reconstruct f through this integral here. We're assuming here for simplicity that both f and f hat are L1 functions. So there's no sort of problem with these integrals. Okay, so really here we have an expression of f, and if we think of omega here as a random variable, then we can come up with at least one candidate for beta. Okay, so looking at the Monte Carlo approximation of the Fourier transform, you can actually represent that using one of these shallow networks that we're looking at here. So let's take K samples. The inverse Fourier transform would look like this, right? So let's define alpha as just the Monte Carlo approximation of the inverse transformation. You have a density P appearing here, and we call alpha hat the f hat divided by P times e to the I omega x. Now the nice thing here is that each alpha hat is an unbiased estimator of f. So alpha is also an unbiased estimator of f. And we can get a sense of the quality of it as an approximator for f by looking at the variance of alpha. Okay, so that's the first theorem here. The variance of alpha is in fact equal to 1 over k expected value of absolute value f hat squared divided by p squared minus f of x squared. And there's a 2 pi factor as well. If we look at this expression here, we see that this f square we can't do much about, right? But we do have a p here, and the p is arbitrary. The p we can choose ourselves. And in fact, we can use this to bound the generalization error of the original problem, at least the optimal one, in this way. So we see here that the optimal solution is bounded by a term that depends only on the expected value of the transform squared divided by p squared, plus another term, which is basically the variance of the noise here. So again, ignoring the noise bit, which we can't do much about, what we arrive at is an expression here where the one thing we have control over is p, the density of omega. And also you see the factor 1 over k here. If you remember the line here, this is the convergence you would expect to see if indeed you have 1 over k as part of the bound for your generalization error. So really we want to get something that sort of follows the red line here. Okay. So what about the density p then? Can we choose it in such a way that we minimize this expression? No, if we minimize this expression, we have a nice sort of upper bound for the error. Note that we can just write what this is. So what we're looking for is a p that sort of minimizes this integral here. And in fact, you can solve that problem, and you can get a sort of optimal density p star, which would be proportional to absolute value of f hat. note that P star is in fact independent of the number of Fourier features and does not depend on the distribution of the data either, which at least I found very surprising when I saw it the first time, and I still do. Okay, so let's see how this works in practice. Let's assume that we're trying to recover some function f that's given by e to the minus 6x divided by square root of 2 squared. And of course, this is picked in a way that we have complete understanding of the Fourier transform here. We observe 20,000 independent samples of x and y. We assume that x is normally distributed, no noise. And we're solving this problem. Well, we solve this problem where we discretized expected values for a range of omegas. Again, omega is a random variable. We generate it according to some distribution, shove it into beta. Now the only unknown is beta hat, the amplitudes. That we can solve by solving the normal equations. And then we vary the variance of omega. So according to this, the optimal density for omega should be proportional to the absolute value of the Fourier transform of f. So that means a sigma of 6. This is what we get. Sigma on the x-axis, error on the y-axis. You see a nice minimum here, sitting precisely at 6. Now, I'd like to say that this is always perfectly true, but you know, the different choices of f might lead to slightly different minimum, but you do typically see a shape that looks like this, where the minimum sits close to the expected optimal density. Okay, so we would like to sample from a density that's proportional to absolute value of f hat. Of course, that's not doable because in general we don't know f hat. I mean, knowing f hat, it's the same as knowing f, and that's really what we're trying to reconstruct. So we don't have access to f hat, so what do we do? Well, what we do is that we propose the following Metropolis algorithm. So you start with some data, x and yn, and you seed your frequencies in some way. We ended up seeding omega with 0. Mostly, I think, because then if it's not 0, then you have to motivate the choice, and it worked nicely with 0, so we sort of picked 0. We define a proposal step. You have some step length delta. You have a standard normal in dimension kd, and you take a random step in rkd. You get some proposed new frequency set. You solve the convex problem, minimizing for beta hat. This is the proposed amplitudes. Okay, and then actually what we do now is that we have k Metropolis tests. So letting small k go from 1 to large k, we take the quotient of the proposed amplitude, with the old amplitude raised to a gamma, and we see whether or not that's larger than R, where R is some acceptance criteria. So the way to think about this test is that, well, if beta is large, then we're more inclined to accept the new step than if beta is small. Then, sorry, if the new proposed beta is large, we think that there's a lot of value to be found for that corresponding frequency set. So we accept it with a high probability. And if it's small, then we typically reject it. Okay, so that is actually how we define the next omega. And note here that we're solving this, the normal equations only once per iteration. And then we update the omega. So we have a choice of updating the different omegas or not. So it's slightly non-standard in that way. We're not just taking one step and then accepting or rejecting the entire set. We have a motivation. We have some sort of justification for how to pick a good exponent gamma and acceptance criteria R. Personally, I think that in practice, you probably want to sort of hand tune those a little bit depending on the problem. Anyway, okay, so let's go back to where we started. So we have the regularized discontinuity, and I'm still missing a minus here. So sine integral x divided by a times e to the minus x squared divided by 2. Okay, let's look at how the Fourier transform of the reconstructed functions sort of evolves as we follow this sort of this Metropolis algorithm. So remember, we seed omega with 0. So at the start, we're just looking at the entire mass is concentrated at 0 here. We go 100 times, and then you see here that there's significant mass all the way out to 100 here. Just for comparison, after about 1 million steps, stochastic gradient descent transform look like this. Everything between -2 and 2. So really, it's a completely different picture here. And after 1,000 steps, we've gone even further out. And finally then, looking at the convergence of the generalization error, we see that we are now achieving the sort of desired convergence rate with respect to k, so with respect to the width of the neural network. And my God, I was very quick. It's only half past.